So for the competition, it's about lumbar spine degenerative classification. So the spine has different parts. The lower part of the spine is known as the lumbar part. So we're going to find if there are any uh, problems in the lumbar part of the spine scan images which are given to us for each patient. Each patient can have three types of scans: sagittal T1, sagittal T2, and axial T2. Normally, dealing with medical images, uh, we have these three directions for taking a scan. The transverse or axial direction is when we take a scan parallel to the ground, and the frontal scan is when the scanner is parallel to your face, and the sagittal is like the cross section. So you can see in this data set, you're not having a frontal scan because when you're talking about the spine is at the back of the body. So we're going to take a slice in the middle like this. The spine will not be visible, so it's not of use that much. So we only use axial and sagittal scans here. We can see there are two sagittal scans here, T1 and T2. This axial is T2. This T1 or T2 generally describes the type of mm, the way the molecules interact with the scanner. For example, there may be different photo molecules or different densities in the human body which interact and give different scan images for different settings. So the machine settings are modified such that in T1 scans, the body parts containing water is dark and the parasital water is lighter. And for T2 scans, the body parts with water becomes light and those without water become a darker color. Hmm. So I will see an example. This is the example given in the data set. All images of a single patient. We'll see this is the sagittal scan T1. Since this T1, the parts which contain water are darker and which don't contain water like bones or white in color. This is the sagittal T2 scan. In this, the water containing parts are lighter in white color we can see here, and the non-water containing parts are black in color. I can see clearly here the this white part. This part is white because the spine is has a cushion-like membrane called membrane inside which there's a fluid called cerebrospinal fluid. Since it contains mostly water, this part is appearing in white color. The settings can be like changed to modify which part of the liquid or which density liquids, how much water concentration should be displayed as brighter and it should display as darker. So, this one is the axial scan, which is like from seeing from top. This part is white part. This is the spine. Mm, So all these images are for a single patient. Why these many images for a single patient? It's because it helps doctor find out where exactly in the spine there is the problem. For example, let's see how the scan is taken for the axial part. The machine scans the first here, then here, then here, then here. So it takes like slice of the body from top to bottom. So there are like many slices which help the doctor find out in which part of the spine the actual problem is there. So if we take n MRI images like this and we combine all of the 2D images as 3D part, it's called as a CT scan. Okay. For the data part, the input which is given to us is the all scan images, and there's also an additional input which is given only for the trained dataset. It is a location of the anomaly. It's where exactly the problem the patient is having is located. It's given so that when we are training, we can train a model to find out which part of the spine the problem is actually there. We'll see this afterwards. An output that is expected is the probability the issue the patient is facing is normal, is moderate, or severe for each of the three diseases which they have said. The three diseases which they have said are foraminal, subarticular, and canal. These affect different parts of the spine, and there are subtypes in subarticular and canal, left and right, because this subarticular could occur on the left side or right side of the spine. Same for canal. So technically, there are five diseases which you have to find out: foraminal, left subarticular, right subarticular, left canal, and right canal. So for three diseases, on which portion of the spine the actual disease occurs. The spine is divided into different regions. The top part is cervical, the middle one is thoracic where the lung occurs, lower one is the lumbar part, and the uh, downmost one is sacral. Our scans and the composition focus only on the lumbar part, so only this part will be displayed in the scan images. We'll only focus on this one. We have to say exactly which part of the lumbar region the problem is. The lumbar region consists of five bone segments: L1, L2, L3, L4, and L5. The green color are the bone segments, and the white color are the spaces where the problems could occur. The problems don't occur actually at the bones, but the spaces between two bones. So problem could be between L1 and L2, or L2, L3, or L3, L4, or L4, L5. So for each of these, we should give the probability it's high, low, or medium. Also, yeah, it will run five places here, 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 L3, L4, L4, L5, or the below L5. Below L5 is called as L5S1. So in five places, which you have to see. So the model which we'll be creating is known as a multi-output, multi-class model. Because we're not having a single output, we have to find for each five parts of the spine if the disease is moderate, mild or severe. Some patients could have the same disease at a lot of, but not in a single part, but in two or three more places. So this is a multi-output model for five places we are predicting, and for each place it can be mild, moderate, or severe. So it's a multi-class classification also. So it's a multi-output, multi-class model. So as I said, there are five diseases. Each one we have to find in which part. There are five options. On each part, there can be three stages: low, medium, or high. So totally 5 into 5 into 3, 75 output probability should give for each patient. So starting off, we'll start with a simple example. We'll mostly using only one scan. Let's take the sagittal scans, which are easier. And since there are many sagittal scans, we'll take the middle one, which has the most information. As you can see, the scans at the edge does not have the spine in it at all, so it's not useful. We'll take only one scan from the middle and use this to find where the issue is actually. And after finding from this one, mostly this will give a good enough accuracy for us, like 70 to 80%. After completing the task with a single image of the sagittal, we'll uh, change the model to include all the images of the sagittal and all the axial and the T2 images in a single model to improve the accuracy. So about the how data is stored, the data is contained in two CSV files. First one is train.csv, which has the patient number, and for each file locations and five diseases, how mild, moderate, or severe the diseases. So each patient, whether it is mild, moderate, or severe, at five locations for five diseases is present in train.csv. But you actually don't get the image uh, image file in this train. You have to take the patient number from that train, go to train series descriptions.csv, search for the same patient number here, and for each patient there can be three scan sites: sagittal, T1, T2, and axial. So you have to choose which one you want. For now we'll be taking sagittal one, so we'll be going uh, train images slash the patient number slash the series ID is the scan type. The first we're taking sagittal T1. So from the train series description, we'll find what is the sagittal T1 series ID for this patient number from this data set, and we go to the folder, and inside of folder I'll be like many scans for the same, sorry, many images for the same scan, different slices. We have to choose the middle one of those, and we'll use for training for now. As you can see, the images are present as .dcm format. .dcm is a medical imaging format which is known as DICOM. In this DICOM format, there is not only the image data but the patient data, the scan type, T1 or T2, which portion of the patient scan was taken, the X, Y, and Z values, which angle the instrument was, what time the scan was taken, and other settings. So for now, we'll take the image data alone for training the model. In the future, if needed, we can take the position of the image and other stuff too. into the model. For now, we'll just image data alone. We can save this image data as a separate PNG, then load for training a model. So before starting with this one, first we'll divide the tasks for the coming 1 week. So the first task will be grad cam. Grad cam actually helps us find out which part of the image contributed most to the output. For example, we'll take the dog and cat classification example. We know the background of the dog or cat did not contribute to the classification. It doesn't matter if the dog was in the park or if the dog was in its house. The model predicts it as still a dog. The model does not care what is the background. It only cares about the face. So if we take the output of the model and backtrack step by step from where the output came, we can actually map in the original input image which parts contributed to most as a heat map. As you can see here, this part Harris will be doing using the cat and dog dataset for now. After this cat and dog dataset, we will use in the spine dataset to find which part of the spine actually contributed to the severity of the disease. The second one will be uh, fake scan generation using GANs. GANs are generative adversarial networks are used to generate fake images like the real ones. Why we are generating fake images for this competition? Let's say there are two patients. One patient had only 5 scans, and the second patient has 10 scans, and the third patient might have 13 scans. But when we're training a model, we need a fixed number of scans. So what we do, we take 10 as the middle number and we fix all the patients should have 10 scans. Let's say the patient has 13 scans, it's not an issue. We can ignore like 3 scans in the middle and we can take the remaining 10 scans. But if the patient had only 7 scans, we have two options. One is to leave the remaining part as empty images, 3 ones. But that will affect how the model is working because we don't know which part of the spine the 7 images were taken and stuff like that. So the better idea is to scale up the 7 images into 10 images to generate an image similar to any given images in the scan. Can use this generative adversarial network which generates extra images for the same patient. So initially we'll just try creating an image which looks like a scan. So we'll take the T1 sagittal images from this dataset and create just an image which looks convincing. Afterwards, in the future, we'll use this to create increase the number of scans for each patient and make it the same number to train the model. This task Electric will be doing. For the third one, as I said before, different patients have different scans. It's important for us to fix the number of scans each patient should have to build the model. So, to understand how much scans are there for each patient, we'll take the count the number of sagittal T1, sagittal T2, and axial scans for each patient and draw it as a distribution histogram like this one. Let's say this is the number of sagittal scan images for each patient. Let's say mm, 5 patients had 10 sagittal scans taken for them. So this 10 will be 5. So let's if you want to find how many patients had 13 sagittal scans taken for them, the count is 2. So from this we can observe most patients have like around 7 scans or something. So we'll fix the limit as 7 and we'll remove extra scans from those patients who have more and we'll fill up scans for those patients which have less scans. So this is the first part of the this task. The same thing for the sagittal T2 and axial 3 graphs to understand the distribution. Hmm, this one, this task will be done by Guhan. And the second part of this task is to create a function which takes in the patient ID, which displays all the scans of the particular patient and prints whether all scans on or prints whether all the output data which is expected, whether the 5 diseases are mild, moderate, or severe. So this is the second part. So yeah, with this it's over.